We introduced the dimension of a vector space as a kind of measure of the size of that vector space. And I said at the time that if this is to be a good measure of the size, it ought to have certain properties. In particular, if you've got a vector space V, which has a subspace U, then the dimension of U ought to be less than or equal to the dimension of V. In this video we'll prove that, as well as some related results. So here is the subspace dimension inequality. It says that if you have a finite dimensional vector space V and a subspace U of V, then first of all, the dimension of U is less than or equal to the dimension of V. And secondly, if their dimensions are equal, then actually U is equal to V. The second part especially is very useful because quite often we'll want to show that a certain subspace of a vector space V is all of V. And part 2 says we can do that by showing that that subspace has the same dimension as V. We've got enough technology now that the proofs are quite short. Let's begin with number 1. So we take a basis for our subspace U. If we think about that as a sequence of vectors in V, then it's still linearly independent. So by the Steinitz exchange lemma, it has a size at most the size of any spanning sequence of V. A basis of V is also a spanning sequence of V, so the size of this basis of U is at most the size of a basis of V. The size of a basis is the dimension, so that's the inequality we want. For part 2, let's suppose that the dimension of U is equal to the dimension of V, and for a contradiction we'll suppose that U is not equal to V. Certainly U is a subset of V, so if it's not equal to V, that means that there is an element of V which is not in U. So let's choose an element, lowercase v, which is in V but not in U. Now if we take a basis B of U, then its span is U. So its span doesn't contain this vector, bold V. By the extension lemma, B, the basis, followed by this new vector V, is still linearly independent. But now we have a linearly independent sequence which is larger than a basis of V. So it's larger than a spanning sequence for V. And that contradicts the Steinitz exchange lemma, which said that every spanning sequence is at least as large as any linearly independent sequence. So we're done. We're now going to prove a result about dimensions of sums and intersections. You'll remember that when we studied finite sets, we had this thing called the Inclusion-Exclusion principle, which told you about the size of a union. If you have two finite sets A and B, the size of the union of A and B is equal to the size of A plus the size of B minus the size of A intersect B. This proposition is extremely similar to that. It says that if you have two subspaces x and y of a finite dimensional vector space V, then the dimension of x plus y is equal to the dimension of x plus the dimension of y minus the dimension of the intersection of x and y. So you can see that dimension really is behaving like a measure of size in the sense that this result is extremely similar to the inclusion-exclusion principle for finite sets. The proof just comes from using the extension to a basis result, which we proved in the last video a lot of times. So let's begin by taking a basis for x intersect y. X intersect y is a subspace of V, so it's finite dimensional, so we know it has a basis. And we'll give a name to that basis, which is z1 up to zk. This is a linearly independent sequence inside x, so it can be extended to a basis of x. So let's do that and introduce some notation for it. z1 up to zk followed by x1 up to xl will be a basis of x. Of course we can do the same for y, so we get a basis z1 up to zk, then y1 up to ym of y, and then it's enough to prove that the z's, x's and y's together form a basis of x plus y. And the reason is because if we've proved that, then the left hand side of that equality would be k plus l plus m, and the right hand side would be k plus l plus k plus m minus k. So if we were to prove that this thing was a basis for x plus y, then this equality really would hold. To prove that that is a basis for x plus y, we must prove that it is a spanning sequence and that it is linearly independent. So we'll begin by showing that it is a spanning sequence. Now every element of x plus y is an element of x plus an element of y. And every element in x is a linear combination of the x's and z's. Every element of y is a linear combination of the of the y's and z's. So adding those two linear combinations together, every element of capital X plus capital Y is a linear combination of the x's, y's, and z's. That tells us that the x's, y's, and z's together are a spanning sequence for the subspace capital X plus capital Y. All we need to do now is prove that the x's, y's, and z's together are linearly independent. So let's suppose we have a linear combination of the x's, y's, and z's equal to the 0 vector. Our job then is to show that all the coefficients in this linear combination must be 0. If we take this linear combination and rearrange it by moving the x's over to the right, then what we get is the sum of the aizi's plus the sum of the ciyi's is equal to minus the sum of the bixi's. But now let's look what we can say. I think I've made a little bit of a typo there and mixed up my lefts and rights. So let's just correct that. Look at the thing on the right. That's a linear combination of x's, so it's in x. But on the right, you have a linear combination of z's and y's. The z's and the y's together were a basis of y, so this is a linear combination of elements of the subspace y, so it is an element of y. Okay, so this left-hand side thing on the left-hand side is an element of x and is also equal to something which is an element of y. So it's an element of x and y. That is, it's an element of x intersect y. But the z's are a basis for x intersect y. So every element of x intersect y is a linear combination of the z's. In particular, minus the sum of the bixi's is equal to some linear combination of the z's. Let's say it's equal to the sum of dizi. But now what we get, just rearranging this equality a little bit, is we get that sum of bixi plus sum of dizi is equal to the 0 vector in V. That is a linear dependence on the x's and the z's. But the x's and the z's were a basis, so they're linear independent. They were a basis for x. So it follows that the b's, and incidentally also the d's, must all be 0. But we could do a similar game with y's instead of x's, and that would prove that all of the c's were 0. And finally, if all the b's and c's are 0, then this expression at the top says that the sum of the aizi's is 0, but the z's were linearly independent because they were a basis of x intersect y, so all the a's must be 0 as well. We've established that the a's, b's, and c's are all 0, and therefore we've proved linear independence of the set consisting of all the x's, all the y's, and all the z's.